Euler's method is a numerical method to solve differential equations. We will do one initially. We'll start with one where we can actually solve using separation of variables, dy dx equals 2x, where we have an initial value of 0, 1. We're going to use a step size of 0.5. This is an iterative method, that is Euler's method, and it uses the idea of making everything short tangent lines. And so here's the setup. We have, we're going to do these 4 iterations, and so we start with 0, 1. We're going to go a step size of 0.5, so every step we go up 0.5, and we want to find out what the y value is when we get to an x value of 2. And so the idea is at 0, 1, the slope will be 2 times 0. It will be 0. To find the rise dy, we do the run dx times the slope. So dy dx times dx is going to give us our rise. So 0 times 0.5 is 0. So to get to our next value, our next height, we were at 1, we go up 0. Well, now we're at 1 again. So therefore, here we are at 0.5, 1. So at 0.5, 1, the slope will be 2 times 0.5. It's 2x, which is 1. The rise then is the slope, rise over run times the run. 1 times 0.5 is 0.5. So from a height of 1, we go up 0.5. Now we're at 1.5. So therefore, when x is 1, the approximate height is 1.5. Now we go ahead and actually find the slope there. So 2 times 1 is 2. We do the slope times the run, which is our rise. 1.5 plus 1 is 2.5. Here's our new height. Continuing in this iterative fashion, we have a slope of 3. Our rise then is 3 times 0.5. So we were at 2.5. We go up 1.5. We're now at 4. So our final answer is 4. This is the segments that go along with this particular problem. This is the idea of dy dx times dx equals dy, and you're always adding the dy to get the next value. What we see is the exact solution. The exact solution you can add to differentiate and solve for c, and you get this parabola. And so we can see that we are underneath the true solution, and we'll talk a little later about errors associated with Euler's method. Here we have a slope field for the differential equation dy dx equals negative x over y, but what I can do is show Euler's method. And so I will, starting from this point here, I'll do one iteration, and we move that amount. And then we can do many iterations, and you can see what happens. Now, of course, the problem we get is it's not going to wrap back around. Euler's method, when you get down to these slopes, which are very large, nearing infinity, such as these vertical tangent lines, well, it pretty much goes off the rails. So that's one issue with Euler's method. Of course, if we make the step sizes smaller, we're going to get more accuracy in general, but still we have problems around vertical tangent lines. So there are some limitations inherent in the method you see there. But of course, the smaller and more tightly packed we make these tangent lines, smaller steps, the better approximation we're going to get. Now this is still one that we can solve using analytic methods, separation of variables, to get a simple family of circles. We can change this though to a different differential equation. Now we have the differential equation x plus y. Simple as it is, it's not something we can do using separation of variables. And here you see the slope field. We can go ahead and do Euler's method, and we see we have this solution. If I drag this around, I can get some very different curves depending upon how we do this. And again, if you bring in the tangent lines together closer, you get a better approximation. Now let's take an actual look at doing this one using the method, Euler's method. So we have dy dx equals x plus y, step size of 0.5. We start at 0, 0. We're going to go to 2 comma something. And so we know then we start at 0, 0. I'm going to go by 0.5, so I can fill out this part of my table from 0 up to 2 by 0.5s, and I have 0, 0. So to start with, I'm not going to use all the columns that were in the other slides, just an x and a y and a little bit of computation. At 0, 0, the slope is 0 plus 0, which is 0. So we have a slope of 0, a run of 0.5, we go up 0. So if we go up 0 from 0, we're at 0. So now at 0.5 comma 0, we have a slope of 0.5 plus 0, which is 0.5. So therefore, slope of 0.5, run of 0.5 is a rise of 0.25. Now we're at a height of 0 plus 0.25, 0.25. At 1 comma 0.25, our slope is 1.25. And so we would do 0.5, which is our run, times 1.25 is our slope, and we add to that 0.25. So here's our slope times our run plus the original amount, which is 0.875, and then finally we find that our slope at this spot which is 2.375, adding these two together. So our slope times our run, we add our previous value of 0.875, and our answer would be 2.0625. Now, is that too high or too low compared to the real value? Now, of course, I can't actually find the real value analytically, but I can still figure out some ideas of the error, and this is the way I would go about doing it. You have to remember that Euler's method is using tangent lines, and so if I'm concave up, Euler's method is going to be under approximating because I'll be below the curve. Tangent lines will be below the curve, whereas if I'm concave down, Euler's method will over approximate. Well, to find concavity, I'll look at the second derivative. So what I do then is I take a derivative of the differential equation. dy dx becomes d squared y dx squared. Derivative of x plus y, well, derivative of x is 1. Derivative of y is dy dx. dy dx is x plus y, of course. So here it is. Second derivative is 1 plus x plus y. At the point 0, 0, actually at all these points when x and y are positive, the second derivative is going to be positive, so I will be concave up throughout this, and so I will be under approximating. Let's try to find that spot. If I move my start value over to 0, 0, you can see that these curves are all concave up, and so it would seem as if I would be under approximating. Another example here. This is dy dx equals x times y, and for something like this, you definitely can get an exact solution, which we'll do below. Starting at 0, negative 1, with step sizes of 0.5, going up to 2, well, whatever we find out it is. Here's the table we initially set up of our x values and our y value. At 0, negative 1, the slope is 0 times negative 1, which is 0. So I do a slope of 0 times a run of 0.5. Of course, I don't go up at all, so I didn't bother to write anything there. At 0.5, negative 1, my slope is negative 0.5 because I multiply. Negative 0.5 for slope times my run of 0.5 is negative 0.25. So I rise negative 0.25, which means I'm going down. So now I'm at 1, negative 1.25. My slope is the product of those two. So slope times the run is the rise. I add this on to my previous height. I'm down here. My new slope would be 1.5 times negative 1.875. I take that times 0.5, which is my run, and I add it to this value, and this is my final answer. Now, what sort of approximation is this? Is this an over approximation or under approximation? Well, if we differentiate dy dx equals xy, this is going to require a product rule on the right. So it's x times the derivative of y plus 1 times y. Now dy dx is xy, so I've got x squared y plus y. That's my second derivative. Now, at least at the point 0, negative 1 where I start, this is a value of negative 1, which is less than 0, so therefore I'm concave down, and I'll be over approximating at that spot. So I expect the real solution to be lower. So we separate variables. dy over y equals x dx. You integrate both sides. Here's our general solution. I plug in the point 0, negative 1 after I'm going to exponentiate both sides, move the constant in front. I'm using properties of exponents. So now I can plug in 0, negative 1. I find out c is negative 1. So here's my particular solution. And if you plug in 2 for x, you're going to get negative 7.389. So clearly, I did indeed over approximate using Euler's method, which makes sense because I was concave up at that spot for this differential equation. So this is a good way to set up your columns of x values and then y values, which are calculated in this iterative method. And once again, as far as looking at errors, the error is going to decrease as the step size, or dx or h, approaches 0. It's going to increase near the vertical asymptotes because you have very large derivatives. It's a linear approximation, an iterated one, so the error relates to the concavity. And again, as I showed a moment ago, you take another derivative of your differential equation to get concavity, and then you try to find out where you are in your table, if you're going to be concave up or concave down. Concave down is an overestimate, concave up is an underestimate because tangent lines would be below the curve.